All right, hello everyone, and welcome to the ATiA seminar. It is my pleasure to have Abby Hickok from UCLA, who's currently visiting Columbia, and Andrew Bloomberg come to us and speak to us about some recent work on TDA for non-uniform data and introducing a family of density-scaled filtered complexes. So please take it away, Abby.
Okay, thank you. Thanks for inviting me to talk at your seminar. My name is Abby Hickok. I'm a fourth-year grad student at UCLA. My talk today is going to be on a recent preprint of mine that's about a new way of doing TDA when your data is non-uniform. Okay, so to start, so this work is about using persistent homology to infer the homology of some underlying Riemannian manifold given a point cloud that's sampled from it. So, I mean, as probably most of you are aware, being at an applied topology seminar, we care about this because lots of data sets lie either on a manifold or near a manifold, or, at least we like to assume that that's true. For example, on the left here, we have an image library where, it's a very high dimensional data set where we can picture each image as like a high dimensional vector where each coordinate corresponds to like pixel intensity. So this is very like high dimensional, but here we have, in this example, these are like pictures of a sculptural face taken from different poses and lighting directions, sort of a famous example. And it's really well parameterized by just 3 dimensions. So we're relying on this like underlying 3-dimensional manifold, maybe, allegedly. And on the right here, we have this example that I like. It's the conformation space of a cyclooctane molecule. And this has been shown in previous work to be the union of, this is a 3D projection, but it's the union of a Klein bottle and a sphere. So in general, lots of data sets lie in a manifold, and we want to understand this manifold structure. So the goal of this work is using pH to infer the homology of this underlying Riemannian manifold, given just a finite point cloud sampled from it from some smooth probability density function f on the manifold. So the problem that I'm addressing with standard distance space complexes is that they're not really built to handle non-uniform data very well. So, for example, in the Čech complex, we at a given filtration level would put a ball of the same radius at every point, regardless of the density of points in different regions of the manifold. Whereas really probably what we should do is put a ball of smaller radius at higher density regions. And that is more or less the idea of these density scale complexes. So there are more naive, simpler solutions to this, like maybe doing like a k-nearest neighbors filtration. And that's definitely, the same sort of intuition. But the k-nearest neighbors filtration in particular has like a robustness problem that I'll show you an example of this later in the talk. And whereas the density scale complexes have a way of getting around this like robustness issue. Okay, so now I'll just give you like a simple example, a synthetic example of non-uniform data, just to have a nice picture in your head for the rest of the talk. So here we have the manifold is this disjoint union of 2 circles. One is much larger than the other. I've sampled uniformly at random from each one, which means that the points are much denser on the smaller circle than on the larger circle. And here I'm showing the balls that we'd have in the Čech complex as the radius increases. And so the smaller ball is of radius 1, so immediately at radius 1, it fills up. And then the balls in the larger circle keep growing until eventually they fill up at the radius 5 circle, they fill up at radius 5. And so, the conventional wisdom of persistent homology would briefly say, well, the homology classes with the longest lifetimes, those are the true features in the manifold, and the ones with the short lifetimes, those are just noise. But if we were to apply that to this example, okay, then we would say, well, the homology class represented by the very large circle, well, this has a very long lifetime. It lasts all the way till 5. Whereas the homology class represented by the small circle fills up, dies almost immediately. So if we were to apply the conventional wisdom, we would say this large circle is a true feature and the small circle is just noise. And of course, that's wrong here. Both of these homology classes corresponding to the 2 circles are like very real features in the manifold. And we have just as much like information about both of them because points are very dense on this small circle. And yet the conventional wisdom gets it like very wrong. So what's going on here is that the Čech complex just isn't homotopy equivalent to the manifold for very long because of this small circle. And this can happen in general, where the Čech complex just isn't homotopy equivalent to your manifold, is only homotopy equivalent for a small range of filtration values. And even when you have lots of data points, that range will increase, like even as the number of points approaches infinity. This is never going to be homotopy equivalent for very long. And so what we end up seeing is that the persistent homology of like the Čech complex or other similar complexes is really like very largely dependent on like topological feature size. Here, like this circle is larger, so it has larger persistence, rather than on maybe how much, information we have about different topological features. So this is especially a problem in a manifold like this, where there are features of different sizes. Or if you're like maybe comparing 2-point clouds sampled from two manifolds of different scales or densities. Okay, so this is sort of another example. Here, this is a Cassini curve, and I've sampled it like uniformly in the angle theta, which leads to having higher density on this little narrow bridge here, and then lower density out here. And you can see if we were to build, Rips or Čech complex here, we mostly see just a figure 8 here. We see these two 1D homology classes, just because these circles in the middle here meet very quickly. But really we have, the points are very dense here at this narrow bridge. We have a lot of information showing us that there's a separation here. This is why visually we can see that's very clear that there's just one closed loop here. So what we'd like to do is put much smaller balls in the denser area. And that way we can actually see that there's just one closed loop here, just one 1D homology generator. And so to do this, what we do is we modify the underlying metric space. So effectively, we're shrinking distances between points in sparse regions of the manifold, and we're enlarging distances between points in dense regions of the manifold. So when you do that, that leads to smaller balls, well, visually smaller balls in dense regions of the manifold. So, and then once we've like modified this metric space, then we can just build like the usual Čech complex or whatever complex you want in this new metric space. So, now that I've given you the gist of this idea, so I'm going to spend the first part of this talk talking about like theoretical properties, and then the second part of the talk talking about how you actually implement this and some examples. So this brings us to like the setup of this approach. So we have we're assuming we have some n-dimensional Riemannian manifold M with the Riemannian metric G. I don't totally know the background of people in this group, so I'll just briefly review the basics of Riemannian geometry. So what a Riemannian metric is, it's a way of defining an inner product on each tangent space at each point. So for example, in Euclidean space, the tangent space can be associated with just Rn, and the canonical Riemannian metric is just the usual inner product. But in general, any manifold can be given a Riemannian metric, so any manifold can be embedded in Rn. If you are a submanifold of Rn, like the sphere here is a submanifold of R3, you can define a Riemannian metric in the tangent space by taking the canonical Euclidean metric and just restricting it to the tangent space. So this requirement of like having a Riemannian metric doesn't at all restrict the class of manifolds that we're studying. We just need to have a Riemannian metric specified. Okay, and then, right, so that was the Riemannian part, and then we have a point cloud X that has n points. This is the notation I'll be using like throughout the talk, sampled from some smooth unknown probability density function f on the manifold. And it's important here that f is non-zero. This is because, of course, like we can't observe regions of the manifold where we're not sampling points. So this is both like a reasonable assumption, and also it is like a technically necessary assumption as well. So the reason we're working in this Riemannian setting, two reasons. First is that this is what turns the manifold into a metric space. So we can define the Riemannian distance between 2 points to be the infimum of path lengths between those 2 points, where the path length is defined using the Riemannian metric. And the second reason we need a Riemannian metric is that it induces this volume form dV that allows us to measure like infinitesimal volumes and actually make a probability measure where the probability of some for L subset A is the integral over A of the probability density function times the volume form. Okay, so now the first step is to take this, I've just left this notation up here in case you forget. So first step is to take this original Riemannian metric G, and we're going to modify it based on the density so that in the new manifold, the points are now uniformly distributed. Okay, so I'm defining this density scaled Riemannian metric to be the nth root, little n here is the dimension of the manifold, of alpha n squared, where n here is the number of points. Alpha n is some scaling factor that I'll talk about later. It grows as the number of points grow, times the density f squared times the original Riemannian metric. So when f is large here, this factor is large, and so we're effectively making distances larger. I think of this almost as like a viscosity term, where like in dense portions of the manifold, things are like very viscous. And so if I were to put a ball at a dense region, it would grow slowly. This is, you can
Sorry, Abby, can I ask a quick question? Yeah, so I just want to understand, can you give some motivation for why alpha of n and f end up being squared? I mean, maybe feeding off that viscosity term, we have like, I know drag usually goes as like velocity squared or something like that, but.
The reason is,
the
reason is because the Riemannian metric is can be used to define squared norms. Let me go back here. You know what, I might even have a typo here. This should, there should be a square root here.
Okay. Yeah. So when doing your like Jacobian right?
The short answer is that when you plug in this velocity vector here, this is the squared norm, and so then you take the square root to get the actual distance.
Okay, cool. Thank you. It wasn't immediately obvious to me.
Okay, yeah, thanks for asking. Okay, where was I? Oh, right. Okay. So yeah, it's easy to just sort of directly check that the points are uniformly distributed in this, what I'm calling the density scaled Riemannian manifold. So the uniform distribution in the density scaled manifold is 1 over, this is my volume of the manifold, times the volume form in the density scaled manifold. And you can just directly check that this is equal to the original density function times the original volume form. So now our points are uniformly distributed. Which makes things work nicely. And this is just an example of a conformally equivalent metric. So two metrics are conformally equivalent if one is a scalar multiple of the other at each point. So here that's exactly true. We're just at every point we're multiplying by this factor here. So I think of this as like sort of just like a local scaling factor. And the one part of this definition I haven't explained yet is this like mysterious scaling factor, alpha n. And yeah, so this can be explained in terms of the coverage radius. So given a point called x in the density scale manifold, the coverage radius is just the minimum radius that balls centered at those points will cover the manifold. And here when I'm talking about balls, I'm talking about, geodesic balls in this new metric. And so there's this very old work that says that there is a threshold radius, denoting it here by r star n, where n is the number of points. In this equation here that I've written is specifically in the density scaled manifold. The threshold radius has this equation in terms of the dimension of the manifold, the scaling factor, the number of points. And above this threshold radius, the balls are likely to cover the manifold, and below them they're unlikely to cover the manifold. And so this scaling factor is just defined to be some strictly positive function, so that it goes to infinity as the number of points increases, and the threshold radius of this density scale manifold goes to 0. So what this first property says is that as the number of points increases, balls in the manifold grow slower and slower. or at a slower rate. The second property says that they grow slowly, but they still grow fast enough so that the coverage radius still goes to 0 as the number of points increases. These properties don't like uniquely define a scaling function, but as long as your scaling function satisfies these properties, you're good. Okay, so now that we have this idea of a density scaled Riemannian manifold, this brings us to a density scaled Čech complex. So the density scaled Čech complex is defined to be, it has these parameters M and G, the Riemannian manifold, the density F, and the point cloud X. And the density scaled Čech complex is just the Čech complex if it were to be built in the density scaled Riemannian manifold. So another way of saying this is that it's at filtration level R, it's the nerve of the set of balls of radius R, where here we're talking about, of course, geodesic balls in this density scaled Riemannian manifold. We can do the same thing, right? We can do the same thing for the Rips complex, where we can define a density scaled version of the Rips complex. I'm denoting it here by DVR, density scaled Vietoris-Rips, with the same parameters, and it's just the Rips complex in this new metric space. And there's nothing special about these two filter complexes. So more generally, if you have whatever your favorite distance-based filter complex is denoted by sigma, we can define a density scaled version of it by saying, let's build this filter complex in this new metric space. Okay, and so all of these density scaled these density scale complexes have two important properties. If you're going to take away anything from this talk, these properties should be it. The first is a convergence property. So this can be stated roughly as, as the number of points is increasing, the range of filtration values where the density scaled Čech complex is homotopy equivalent to your manifold, this is going to grow, increasingly large, at least in probability, as the number of points increases. And this is something that we saw the usual Čech complex did not have. And the second important property is this invariance property. So the density scale complexes are invariant under global scaling. So if I scale my point cloud up, my density scaled filter complex is going to remain the same. My persistence diagram is going to look the same. More generally, they're invariant under any conformal transformation. So yeah, a conformal transformation is a diffeomorphism between two manifolds so that the pullback of one of these Riemannian metrics is a scalar multiple of the other. So global scaling is like a special case of a conformal transformation. I usually think of a conformal transformation as a transformation that's like locally scaling the manifold. And so unlike usual complexes, which we saw in the example at the beginning with the two circles of different sizes, usual complexes are like very sensitive to things like scaling. Whereas the density scale complexes have this invariance property. So now, yeah.
All right, just quick question. So I guess for this convergence property, are you going to remind us what does it mean when you have a property in probability? What is that? What does that exactly mean?
Oh, yeah. I'll state it more clear, more precisely on the slide.
Okay,
good question.
Yeah.
Anticipating the slide.
All right. Yeah. Awesome.
Okay. So because you're right that's not a very precise statement at all. Okay, so here I've just written here the density scaled Riemannian metric here at the top, and as a reminder, it depends on the number of points n. So the convergence property can be stated in terms of the convexity radius and the coverage radius of the manifold. So let's let R convex n be the convexity radius of the density scaled manifold. So when R is less than the convexity radius, geodesic balls of radius R are geodesically convex. So intersections of them are also convex. And so they're either contractible or empty. And so we can apply the nerve theorem. let's have here the coverage radius of the point cloud denoted here by R cover N. So this is the minimum radius at which these balls cover the manifold. And then what this convergence property actually says is that when R being the filtration value, when R is bigger than the coverage radius, but still less than the convexity radius, the density scale Čech complex at filtration R is homotopy equivalent to the manifold. And the convergence property part comes from the fact that as the number of points increases, we have that the coverage radius is going to 0 in probability. That's the improbability part. And the convexity radius is approaching infinity. Okay, and so whenever we're in between the coverage radius and the convexity radius, we're homotopy equivalent to the manifold. And this last part about the behavior of the coverage radius and the convexity radius, this comes exactly from that scaling factor alpha n. So we define the scaling factor alpha n exactly so that we would have these properties.
Sorry, can I just repeat back to make sure I'm understanding how convexity radius is defined? So this is the radius at which, if you take any point in your manifold, the geodesic ball of that radius is convex, meaning, and I guess convexity.
Yeah, like the geodesic is contained in the ball.
All right, so for any 2 points in my ball, and I look at the geodesic, that remains in the ball. Interesting. Okay. Cool. And then I guess like the improbability would be something like the places where the ball is not, let's say, geodesically convex, or it consists like the measure.
So the probability, yeah, the probability part is really just for the coverage radius.
Oh, okay.
So the convexity rate, the convexity radius is like an intrinsic property.
Okay.
Of the manifold. The coverage radius is the probability part, because of course you could pick some point cloud where it doesn't cover, but in probability, this coverage radius is going to 0.
Okay, cool, great, thank you. That helps clarify what's going on here for me. Thank you.
Cool. Okay, right, and so the usual Čech complex does not have this convergence property. It does have a theoretical guarantee. This is, I think, a well-known result from like Weinberger et al. So we can talk about the theoretical guarantee it does have in terms of the reach of the manifold. So at any point in the manifold, we can talk about the local feature size at a point. This is its distance to the medial axis, which is the closure of points in the ambient space that have more than one nearest neighbor in the manifold. So in our example from the beginning, the centers of the circles would be part of the medial axis, and the local feature size at a point would be the radius of the circle it's on. And then the reach of a manifold is just the infimum of the local feature sizes. So we have this nice result that the Čech complex at filtration level R is homotopy equivalent to the manifold when R is less than some constant times the reach of the manifold, and also assuming we're sufficiently dense. But of course, this is like not a very good guarantee when the reach in the manifold is small. And that was the problem that we had in the example at the beginning, is that the reach is small here and we can't improve our situation by sampling more points. We're just stuck. So the ordinary Čech complex, as well as other complexes, don't have a convergence property like the one that I just stated before. Okay, so that second property I wanted to talk about is this invariance property. I think this needs a lot of unpacking. So let's say we have some distance space filter complex sigma. If you want, you can just let it be the Čech complex or the Rips complex. Let's say it's invariant under global isometry. And then what the invariance property says is that the density scaled version is invariant under conformal transformations. And I will unpack this, starting with that last part. Okay, so let's say we have some conformal transformation between manifolds. For simplicity, my picture here is just a global scaling of a circle. If we have some point cloud in M1, then its preimage is also a point cloud in M2. So that's what we have here. These are the same point clouds, just scaled down. Okay, let's say little f1 is the density function that X was sampled from. So that would be the density on this big manifold here. And then I could define F2 to be the density function, so that if I were to sample a point cloud from this smaller manifold here, that would be the same as taking a point cloud on the bigger manifold here and pulling it back to a point cloud on the second manifold. So F2 is defined to be basically the density of this the pre-image of the point cloud. It's like what it should be. Okay, and so what the actual theorem says is that the density scaled version of the complex with these parameters from the first manifold, M1G1 F1 point cloud X, this is going to be isomorphic to the density scaled filtered complex with the parameters from the second manifold, the pre-image of the point cloud. So that is like their persistence diagrams will be the same.
Cool. Yeah, so just to clarify, like an isomorphism of filtered complexes would be like a map back and forth such that carries sort of filtration from one to the other one.
Yeah, exactly. Thanks for clarifying this, because I don't mean like topological isomorphism. I really mean something stronger, which is like combinatorial.
Yeah, cool. Sorry, quick question. Maybe this is obvious, but with these conformal transformations, is it clear that they're always injective?
They're diffeomorphisms.
Okay, yeah, okay, got it, yeah, all right, thank you.
Okay, yeah. Okay, and then I'll just quickly unpack this other part, which is the invariant under global isometry part. Okay, so this just means that if I perform some sort of isometry on my point cloud, like rotation or reflection, then my filtered complex isn't going to change. So I think pretty much every complex that I can think of has this property. You know, for example, the Čech complex, the Vietoris-Rips complex have this property that it doesn't matter if you perform some global isometry on your point cloud, you're still going to get the same result. Okay, and then, so standard filtered complexes really don't have this invariance property. They are very sensitive to things like scaling. So if I have the same sort of scaling homeomorphism here, I can show you what I get for this example when I compute the Rips complex. Of course, the underlying manifolds are homeomorphic, but the filtered complexes for X and its image are definitely not isomorphic. So here, in the first persistence diagram, they look sort of similar, but the axes are different. We have this 1D homology class that dies almost at almost 2, and whereas on the right here, it dies at 3.5 or something. It has a much longer lifetime on the right-hand side than on the left-hand side. And of course, we could imagine scaling by even greater magnitudes to make the bottleneck distance between these two diagrams arbitrarily large. So standard filtered complexes really are very sensitive to things like size, whereas the density scaled complexes are not at all sensitive to things like size. Okay, so those are the theoretical properties. So now I'm going to talk about how you actually go ahead and implement this. So I've only implemented a version of the density scaled Rips complex. And the first step here is to estimate the density function as f. And I do that here by doing kernel density estimation. The second step is to estimate the pairwise Riemannian distances in the density scaled manifold. So I'm going to let this d hat denote the estimated Riemannian distance. And then the implementation of the density scaled Rips complex, which I'm denoting here by dvr hat to denote, that's an estimation. This is the Vietoris-Rips complex built in the metric space defined by the estimated Riemannian distance. So that is, we have a simplex, we include a simplex in the complex at filtration level T if the estimated Riemannian distances between all the vertices are at most 2 times the filtration level. Okay, so I'll talk a little bit more about each of these 2 steps. So in this first step, we're estimating the density function f using kernel density estimation. So this is the result on the Cassini curve that I showed you at the beginning, where the density is much higher at this narrow bridge here and less dense, on the sides. Something to note here is that kernel density estimation on a manifold requires knowing the dimension n of the manifold. You do not want to do kernel density estimation using the dimension of the ambient space. You will get the answer wrong. So right, so this implementation does require knowing the dimension. You know, there's lots of work on dimension estimation. You know, for example, like local PCA is one way you can do it, or whatever your favorite method is, but you do need some estimation of the dimension. And the second step of this implementation is to estimate these pairwise Riemannian distances. So the way I've been doing this is more or less the same way that isomap does it. Isomap is a nonlinear dimension reduction algorithm. So first step is to construct a k-nearest neighbor graph on the points in the point cloud. Second step is we define this to be a weighted graph. So given 2 points xi, xj in the graph, I define the weight of an edge to be the Euclidean distance between the 2 points multiplied by this factor here, which should look very similar to the scaling factor I had for the Riemannian metric. It's the nth root, n is the dimension of the manifold, times the scaling factor times the maximum of the estimated densities.
So sorry, Abby, just quick question. So that k-nearest neighbor graph, that just says that, you know, 2 nodes are connected by an edge if they're each k-nearest neighbors of each other, or in the top
yes.
k
Yeah, yeah, thank you.
Yeah, no, it's just been a long time since I looked at isomap. But yeah, all right.
Yeah,
perfect.
For some choice of k that you have to choose.
Right. Yeah. Obviously.
Then yeah, and so the reason the weights are defined this way is because, well, when xi and xj are close, Euclidean distance is a good estimate of geodesic distance in the original Riemannian manifold, and then when we multiply by this factor here, we get a good estimate of the density scale of Riemannian distance. So in fact, as xi and xj get closer to each other, the ratio of this weight and the actual Riemannian distance in the density scale manifold, that ratio will go to 1.
And that's a theorem somewhere?
That's actually not hard to show.
Okay. Well, I have no idea. All right, makes sense. I guess just looking at it.
Yeah, I don't think I actually have like a proof in the paper, but it's true.
Okay, cool.
Yeah.
Maybe a reviewer.
Mostly relying on the fact that Euclidean distance is a good estimate of Riemannian distance when the points are close.
Okay.
Abby, I have a question.
Yeah.
When you introduced this G tilde before, you had this when you had some exponents of 2. You were looking at alpha n squared and f squared. So where have the squares gone here in this estimate?
Oh yeah. Okay, this is sort of related to Justin's question at the beginning. So right, the Riemannian metric can be used to define like the squared norm of a vector in a tangent space. And so then when you want the like actual distance, you end up taking the square root. And so in the Riemannian metric, I have the squares, and then we take the square root, and so the squares go away.
Okay, thanks.
Okay. Okay, and then so my estimate of Riemannian distance is then between any 2 points is the length of the shortest path in this weighted graph. And then if there's not a path, you know, if they're in different connected components of the graph, we just set the estimated Riemannian distance to be infinite. Okay, so the implementation is stable. So, you know, if y is a small perturbation of x, then the 2 filter complexes are epsilon interleaved, so their persistence diagrams will be similar. This does technically require another condition on x, which is that it's in general position, but this is when things, you know, it's random. This is almost surely satisfied. So I don't worry about that. It's also designed to handle outliers in the data. So this is not like the primary reason that I'm defining density scale complexes, but of course, whenever you have a real life data set, you can expect that there probably will be some outliers. So we need to be able to handle them. And so the issue here, you know, the thing that you might worry about is that if I have an outlier in my data, the density is very low at an outlier. And so you might worry that we're going to underestimate distances between outliers and like actual points in the manifold. You might worry about like connecting too quickly between to the outlier. So the reason this doesn't happen is specifically because when I define the weight of an edge in that k-nearest graph, instead of using like an average of the two estimated densities, I'm just using the maximum. So that means that if, say, xi is an outlier, the density is very low here. It doesn't matter because we're using the maximum. So it doesn't matter that one of these is very low. So that means if I do have an outlier somewhere, its ability to connect to points actually in the manifold is going to be limited by the density on the manifold. And I'll show you one example that has some outliers to show you that things don't go like horrendously wrong when that happens. Okay, so now this brings us to some examples. So I want to start with the example that I showed at like the very beginning, where we have these two circles of different sizes. We've like uniformly sampled from each circle. And what we would like is, because these are pretty much both circles at the same space, we have like equal amount of information about both them. We would like to put these two homology classes on more or less like equal footing. Okay, so in the Rips complex, this doesn't happen. We have these two 1D homology classes, and one has a much longer lifetime than the other. Same thing with the 0D homology classes, where only one of them is infinite. Whereas on the right here, this is the density scaled, the approximate density scaled Rips complex. We have the two 1D homology classes are now, they're not exactly the same, but they are much closer in birth and death value than before. And now we have two infinite 0D homology classes, which like correctly corresponds to having two connected components in the actual manifold. So I want to talk about this gap here a little bit. So yeah, theoretically, there shouldn't be a gap here at all. They should have the same birth and death value. The reason for this gap is mostly like error in the density estimation and error in the Riemannian distance estimation. So this is an error in the estimation of those two things that leads to this, but theoretically they would be the same. And you can see here, these 2 points are like much closer than they are in, you know, the Rips complex. So this next example, this is also an example that I showed you a little bit at the beginning of the talk. It's a Cassini curve. I think this example is a good illustration of the conformal invariance property. So here, the point cloud is sampled from the Cassini curve. It's uniform in the parameter, the angle theta. So another way of thinking of this is I've sampled uniformly from the circle, and then I've mapped it in a way that's conformal to the Cassini curve. And so if we were to take the Rips complex and compute its persistence diagram, this mostly sees, it more or less sees a figure 8 shape. It sees these two 1D homology classes, one corresponding to each of these almost poles here. You know, so if I didn't know what this space actually looked like, I might think this is just two disjoint circles or something like that. Whereas the density scaled Rips complex really can see that this is just one 1D homology class, that this is just one closed loop. And this, you know, correctly corresponds to like the actual topology of the Cassini curve, whereas this one from the Rips complex really does not correspond to the, does not reflect the actual topology. Okay, next example. This is also a two-way example, but this is a case where we have some outliers in the data. So I've sampled, I think this is 200 points from a circle and then like 10 points from the square that contains it. So we have some just points in the interior here and over here. And this is mostly not an example to show you that the density scaled complex does better than the Rips complex. This is mostly an example to show you that things still work when there are outliers. So you can see here that we, even with the outliers, we still see this one very persistent 1D homology class corresponding to the actual circle here. And again, like the reason you might worry about outliers is because you might worry that, you know, points in the middle of this circle here are going to quickly like connect to points on the outside and like fill up the circle. That would be like the fear, and that's just not what happens. Okay, Fourth example, this is an example to show that we can pick up on like clusters when they have different densities. So here, this point cloud is sampled from like 2 disjoint squares. On the right here, the density is 5 times as high as the density on the left. And what we see in the Rips complex is that we do see these 2 0D homology classes corresponding to 2 clusters, but only one of them is infinite. Whereas on the right here, we see like really 2 infinite 0D homology classes. So there's like a 1-to-1 correspondence between the 0D homology classes and the clusters in the point cloud. You do also see these 1D homology classes, but remember these are actually pretty close to the diagonal. It's just the way that the persistence diagram is visualized that these look very persistent.
And should I think of most of those blue H1 classes as coming from the left-hand square, or?
A lot of them are coming from like also like points connecting here and making cycles.
Yeah.
But yeah, I mean, but relative to these 2 classes that are infinite, you know, these are pretty close to the diagonal.
Got it. Cool. Thank you.
Yeah.
Why do you have these infinite classes? Is this just because of how you chose your scale parameter for building the neighborhood graph?
Yeah, this is based on the connected components in the nearest neighbor graph. And yeah, this is an example where I also want to talk about the k nearest neighbors filtration. So this is maybe, if you were to think about how to handle non-uniform data, this is probably the first thing you would think of. So in this filtration, at the k filtration level, we would connect each point to its k nearest neighbors and then increase k. So what happens here is that we do see these 2 pretty persistent like 0D homology classes, but we also see all these 1D homology classes, and these are not very close to the diagonal. These, you can see, you know, some of these 1D homology classes have persistence almost as long as this 0D homology class, which is this 0D homology class is a very real feature of the manifold. It corresponds to one of these clusters here, whereas, you know, of course, there are no actual 1D homology classes in the underlying space. And so, you know, what's happening here, the reason that we're seeing these is because points on this left square here are connecting over to the right side before holes in the left cluster have had like a chance to close up. But like more generally, the k nearest neighbors filtration can have a problem whenever we have a situation like this where 2 parts in the manifold are maybe like close in Euclidean space but far away in Riemannian distance, especially when like one of those regions has a density that is much lower than the other. Okay, so this is my last example. This is a real example, sort of. So this point cloud is coming from the Lorentz dynamical system. So this is a dynamical system that models atmospheric convection. I've put like the equations of motion on the right here. My system parameters are just standard system parameters. And you've seen dynamical systems at all. You've probably seen a picture of this attractor, which has, you know, these 2 like very visible holes that correspond to 2 equilibrium points. And so actually, the point cloud that we're going to be dealing with here is actually coming from a time delay embedding of the x coordinate. So I've put a picture on the left here of a 2-dimensional time delay embedding. Using 2 dimensions is the standard. And you know, by Huygens theorem, this is the image of the time delay embedding is still diffeomorphic to the attractor. So we're still looking at the same space. You can see there's still these 2 holes. You can see that one of the holes is much smaller than the other, but the density is also higher to like compensate. So we still have like lots of information about this small hole. I should note that the reason we're not just looking at the attractor itself is not because the density scale complex doesn't do well in the attractor. It does do well in the attractor itself, but the Rips complex also does well on the attractor. So that would be sort of a boring example. Okay, so now I'll show you the result. So on the left here, we have the Rips complex. The Rips complex really only sees one of those holes in the time delay embedding. We have this one very persistent 1D homology class, whereas the density scaled version really can see there are these two 1D homology classes that really stand out in the persistence diagram. And those correspond to the two equilibrium points in the dynamic system that the Rips complex really doesn't see in the time delay embedding. Okay, so before I conclude, I also want to talk about something that's related, at least similar in spirit, are weighted complexes. So another
Sorry,
thing
I have one quick question.
Yeah.
When you have the error that would make like one of the 1D homology classes seem like lower than the other, is the one that's lower always the one that in the original one was close to the birth death? So like when you have the small circle and the big circle in your system, is the big circle the one that has is still staying high and the other one is kind of like come up a little bit, or do they ever like flip roles because of the density scaled metric?
Yeah, so it definitely depends on the point cloud. So if it's totally possible that if the density here in the small circle were so much higher than in the larger circle, then the smaller circle could be the one that's more persistent. It really does.
I guess I was asking, did
yeah.
that happen in your examples, or do you know? Or I'm just curious.
Oh, okay. So in this example, the smaller one is still the smaller circle,
Sure.
and that's just because the density was high here, but not like quite high enough to.
That makes sense. Yeah. Okay. Thank you. Sorry.
Yeah. No. Good question. Thanks. Right. So I was talking about weighted complexes. Right. So you could define like sort of a density weighted complex where we have this at each point we could define like a radius function to be t divided by the same factor that I used to scale the Riemannian metric. And then we could define this like density weighted Rips complex by saying x and y are connected at filtration level r. At t, I mean, if their Euclidean distance is less than the sum of their radius functions. So this would be like simpler than what I'm doing, but it doesn't work very well when there are outliers. So this is the same point cloud I showed you before. What happens here is that at points of low density, so where the outliers are, those balls grow very quickly and they just completely engulf all the points that are actually on the manifold. So, a density weighted complex, while simpler, really doesn't have the robustness properties that you would want it to have to use for like real data sets.
Is that all that goes wrong? Could you prove your theorem?
Well, it's not, yeah, so it's not, so this same sort of issue is going to happen if you have like, even if you don't have outliers, but maybe like maybe you have a manifold where like two regions of the manifold that are close in Euclidean space and one is like low density and one is not. The same sort of thing is going to happen there where like points in the low dimension region, those balls will like grow quickly and engulf the other ones. Like for example, you can imagine even not just on a circle, no outliers, but points are much denser in the upper hemisphere than on the lower hemisphere. Then points in the lower hemisphere would just grow so quickly and like engulf all the ones in the upper hemisphere.
Got it. Okay, so that makes the theorems fail then for this complex.
Yeah, this is not a good complex, is what I'm saying. Okay, yeah, so some related stuff from a slightly different discipline. UMAP and CISOMAP are these nonlinear dimension reduction algorithms. And they have more or less the same philosophy as what we're doing here. So UMAP is this like uniform manifold approximation projection for dimension reduction. This is like used all the time in manifold learning, and its philosophy is what this is from their paper. UMAP attempts to discover a manifold in which your data is uniformly distributed, and that is exactly what we did here, where we defined a Riemannian metric, where in the new metric things were uniformly distributed. And I maybe won't go through the details just for time. CISOMAP, not used as often, is also sort of similar in spirit, although they don't really say this. But in C-isomap, their idea is they're approximating the distance between xi and xj to be their Euclidean distance normalized by the geometric mean of their kth nearest neighbor distance. And this kth nearest neighbor's distance is like asymptotically proportional to the inverse of the nth root of the density. So it is like very similar to the distance estimation we're doing here, where we're modifying by the nth root of the density. Okay, so all of these things, while like coming from different places, are coming from the same philosophy of like, it's better when your data is uniform, things work better. And so just to sum up, I think the reason that density scale filter complexes are good is that it's a better way of dealing with data sets that have locally varying density. I think this is like important when you're comparing point clouds that have different densities, or like when your manifolds have different scales and you're trying to compare them, or when you have like different feature sizes within the same manifold. I think this is important. I think for future work, the most like obvious next step is to extend this construction to spaces where maybe the intrinsic dimension is varying locally. So, you know, a very like simple example of this would be if I have like two manifolds that are, if I have the union of two manifolds of different dimensions, or even maybe your point clouds really are sampled from one manifold, but your dimension estimate is varying across the space, right? Because dimension estimation is like very noisy. And this is actually not so hard to do. We didn't really ever use the fact that we had this like global intrinsic dimension. The places we used the dimension were for density estimation. And for that, you really just need a dimension estimate at the point. So that works fine. We also used dimension when we were in the implementation. We had this like weighted graph, and we used the dimension estimate when we were defining the weight of an edge. So for there, if you had a dimension estimate at two vertices, you know, you could use some sort of average of the dimension estimate of those two vertices. So doing this where you don't have like a global intrinsic dimension, this is actually not so hard to do. The other thing is it'd be nice to like improve this so that they're invariant not just under like conformal transformations like scaling, but maybe a wider class of diffeomorphisms. So here, like in this setting, conformal invariance was the best we could do, because the Riemannian, the density scaled Riemannian metric was conformally equivalent to the original metric. So we can't do any better with this construction. But you can imagine a diffeomorphism that like stretches your tangent space in certain directions more than others. So this is something, and this is sort of like a silly picture here to, you know, seeing what happens at some tangent space. And so here, maybe one way of dealing with this would be doing something with like some notion of sample covariance here, in addition to just density. And right, so maybe to finish the talk, I'll just point you guys to, I have a preprint on arXiv. I also have some code on Bitbucket if you want to like play around with this yourself. And that is the end of my talk. Thanks for listening.
Let's give Abby a round of applause. I'm gonna stop the recording.